Okay, listen up. So yesterday we ended the class. We had talked about how you name simple ionic compounds, right? And then we went into what happens when you have a metal that has more than one possible charge. Okay? Now, we said the general rule for naming ionic compounds is that you name the metal first, and then you name the nonmetal, and the nonmetal needs to end in "-ide". Okay, so that's for simple ones. Okay, once in a while on your periodic table, you encounter a metal that has more than one possible charge. You only use Roman numerals for those metals. Okay, this doesn't apply to all metals, just the ones with more than one possible charge. Okay, they're all kind of in the middle there around iron. Okay, the problem we said we had was that this compound, FeO, and this compound, Fe2O3, could then possibly have the same name. All right? We don't want them to have the same name because they have very different chemical and physical properties. So we got to have a way to tell them apart. Okay? The way we do that is we indicate which charge the iron had in that compound. And then people will know, all right, if this is iron 2 oxide, it's this stuff. There's only one way iron with a 2+ charge can end up with oxygen. Okay? And there's only one way iron with a 3+ charge can end up with oxygen. Okay? So what we did is we said we look at always the non-metal. That's how we figure out which Roman numeral to use. We look at the non-metal. In this case, oxygen is always a charge of -2. Okay? It only has one possible charge. If all compounds have to end up having a charge of 0, the charge on this iron has to be +2. Right? That's the only way that they're going to add up to 0. So ones like that are easy. Okay? Then we know, all right, I write that this is iron 2 oxide. All right? For one like this, we still do the same thing, except now we're going to have to do a tiny bit more math. Okay? Oxygen's always a -2, and there's how many oxygens here? 3. So we have 6 negative charges in total that need to be balanced off by the 2 irons that I have. So this iron has to have a charge of +3, because +3 times 2 is +6. Now these add up to 0, and I know that this stuff is iron Roman numeral 3 oxide. Okay? Everybody follow me there? Right? That's how we have to do it. I have a number of people who tell me, oh, Mr. Coder, I can just reverse the swap and drop. This is a 3, that's a 3. Okay, that'll get me the right answer. It will, maybe 2/3 of the time. Okay? There are times when that's not going to work. Like, for example, with this. Okay? What's Mn stand for? Nope. Magnesium is Mg. This stuff sounds like magnesium. Manganese, right. This is manganese. And what are the 2 possible charges for manganese? 2 or 4. Okay? So, this stuff, okay, is manganese 4. If I just reverse the swap and drop, I would say that this is manganese 2, but I'd be wrong. Okay? Every oxygen has a charge of -2, and there's how many of them? 2. So how many negative charges do I have? 4. Okay? That means this single manganese has to have a charge of +4. All right? The reason that happens is when we drop and swap, okay, if manganese is +4 and oxygen's -2, we go 4 and 2, but we don't leave it that way. We always do what with ionic compounds? Just like fractions. You reduce them to their lowest term. All right? And so that's when just reversing the swap and drop will get you the wrong answer. And it happens at least 1/3 of the time. Okay? So you don't want to just reverse the swap and drop and hope that you'll be right 2/3 of the time, because I'm a jerk and I'll make sure I use more than that. Okay? And the percentage will end up being a lot less than 2/3. All right? Everyone follow me there? Okay. So what we're going to do is just practice a couple of those so we get the hang of how to figure out which Roman numeral we need to put in the name. Okay? Now remember, you don't have to do this for all metals. You only have to do it for metals that have more than one charge. Okay? So you have to look on your periodic table when you're naming an ionic compound and check, am I going to need a Roman numeral here or not? Okay? More often than not, you won't need one. Okay? All right, so let's have you guys try. We already did number 1, but we'll just quickly review it. Okay, oxygen's always -2. 3 times -2 is -6. So I need to get 6 positives. +3 times 2 is 6. This is iron, Roman numeral 3, oxide. All right, so let's have you guys do 2 through 4. Okay, do 2 through 4. Stop after 4. Okay, in case you've forgotten your Roman numerals. 1 is I, and 2 is I. 3 is I. Okay, 4 is IV. Okay, and 5 is V. 6 is VI. And I can't imagine you'll have to go higher than 7, VII. Okay, so I'll give you a couple minutes. Try 2 through 4, and then we'll go through them together. Okay, so for number 2, okay, we've got CO, which stands for cobalt, and S that stands for sulfur. All right, so we're going to start out by just writing out, okay, the names, and then we'll worry about what Roman numeral needs to go in there in a minute. Okay, we've got cobalt something sulfide. Okay, that way we've got that part worked out. Okay, if I want to figure out what charge cobalt has, I always look at the nonmetal. And I remember that my negatives have to equal my positives. All right, so there's only 1 sulfur here, so there's only 2 negative charges. That means cobalt's charge has to be 2, +2. So this is cobalt 2 sulfide. Okay, everybody following me there? 2 sulfide, yeah. Iron 3 oxide, exactly, yeah. Okay, for number 3 here, we've got manganese with chlorine, so that's manganese chloride, but we do need a Roman numeral because manganese can be 2 or 4. Okay? Chlorine is always a -1 charge, and there's how many chlorines? 4. All right, so we got 4 negatives and only have 1 manganese to get rid of them with, so manganese has to be +4. So this is manganese IV, okay? Manganese 4 chloride. And then for number 4, okay? Cu stands for copper. And S still stands for sulfide. So we got copper sulfide, and sulfur is always a -2. There's only 1 copper here, so copper's charge can't be 1 this time. It's got to be 2. Copper 2 sulfide. Okay. Is that making some sense? All right. Finish those up. Go to number 10, then we'll go through the rest of them together in a few minutes. All right, let's look at 5 through 7 here, just so we kind of see how we're doing. All right, so with 5, we've got tin and we've got tellurium. So our name is going to be tin something telluride. Okay, now we got to figure out which Roman numeral goes here. Tellurium is always a -2 charge. Tin can be 2 or 4. Okay, so in this case, since there's 2 telluriums, I've got a total of 4 negative charges, -2 times 2. Okay, if I want this thing to work out to 0, my only tin has to have a charge of +4, so this is tin 4 telluride. You don't. This is just, that's the only way it shows up. Okay, tin can have, depending on how, because most metals come from ores, the structure of the ore kind of determines the charge that the metal you get from it will have. Not really, no. Okay. I mean, once the ore goes through metallurgy and it turns, they've separated all the other minerals from it, it's not going to go into solution. It'll probably just have 1 charge. Okay. But in nature, where you don't have the metal in its pure form, it kind of depends what it's with, what charge it'll have then. Okay, all right, so for number 6, okay, we've got mercury and astatine together, so this will be mercury astatide. Okay, but mercury has more than 1 possible charge. Astatine is always a -1. Right? So there's 2 negative charges here, -1 times 2. Since there's only 1 mercury here, this mercury has to have a charge of +2. Okay, and then for 7, we have polonium iodide. Okay, but we need a Roman numeral on the polonium. Oop. Okay, and iodine's always -1. So that means the polonium has to be +4. Okay, how many people are done up to 10? Okay, I'll give you 1 or 2 more minutes here, and then we'll go through those. All right, let's look at the rest of these. So we got number 8 here. We got antimony, that's Sb, okay, with sulfur. So we got antimony sulfide. All right, so sulfur is always a -2, which gives me how many negative charges? 6. Okay, so I've got 6 negative charges, which means I need to get 6 positive charges from the 2 antimonies I have here. So each antimony then has to have a charge of +3. 6 divided by 2 is 3. Okay, so this is antimony 3, okay, sulfide. All right, number 9, I've got nickel with nitrogen. So the name will be nickel something nitride. Okay, nitrogen is always a -3 charge, which again gives me 6 negatives in total. Okay, so I have to have 6 positives, which makes each nickel 6 over 3 is 2. So that's nickel 2 nitride. And then last one here, ruthenium oxide. Okay, oxygen's always a -2, so that gives me 4 negatives. That means ruthenium, since there's only one of it, has to be 4. Okay, is that making sense? Okay, it's basically the same every time. Anybody need those anymore? That's a 3. Sorry, yeah, and my penmanship is terrible. I told my grade 6 teacher, everyone's going to be using computers. We'll never have to write by hand. I was partially right. I never took into account that I would actually have to use a computer to write by hand. She gets the last laugh, I guess. That's harsh. Harsh. Really harsh. Okay. That's like he who dies with the most toys still dies. Okay. Okay. All right. So for molecular compounds, okay, a molecular compound is made up of 2 nonmetals. Since nonmetals all have negative charges, there's no balancing of electrons, no balancing of charges that goes on. Okay. What we have to realize is that molecular compounds have a very different bond than ionic compounds do. Okay? We said for ionic compounds, their bond is pretty weak. Once they get what they want, there's no reason for them to stay together. Okay? But molecular compounds are stable. Okay? They very much want to stay together. They have to share their electrons in order to have that full outer shell we were talking about all the ionic compounds want to have. Okay? Because they can't possibly give away enough electrons to get a full outer shell, they have to share them. So in something like water, okay, which is what we've got here, hydrogen, its outer shell can only hold 2 electrons, but it starts out with only 1. So pairing up 2 of them with oxygen fits pretty well. It shares one of its electrons with oxygen, it shares one of oxygen's electrons, and kind of has a full outer shell. Okay, same thing down here. Oxygen does the same thing with another hydrogen atom. Now oxygen kind of has a full outer shell of 8, and both hydrogens kind of have a full outer shell of 2. Okay? But the only way that they can maintain that is if they stay together. So molecular bonds, or what we call covalent bonds, okay, are really, really strong. Okay? These kind of compounds are very much going to stay together. They tend to be a lot less soluble in water because of this. Okay? So other molecular compounds, like let's say vegetable oil, butter, okay, things like that, they don't dissolve in water very well. They don't split into positive and negative parts. They have to hold on to each other for dear life in order to keep those electrons there. Okay? Everybody with me on that? Okay. The good thing about that, makes naming them a lot easier. All right? We don't have to worry about Roman numerals. We don't have to worry about dropping and swapping. We just got to write the 2 names, okay, with some prefixes that tell us the numbers. Right? So as long as we can remember our prefixes from 1 to 10, we're pretty much set. Right? So maybe we should write down our prefixes from 1 to 10 just so we remember them all. Okay? All right. So prefix for 1 is mono. Prefix for 2, di. Prefix for 3, tri. 4, tetra. 5, penta. 6, hexa. Oop, I was going to write 7 there. Okay, 7, hepta. Make sure you write it that way. Mr. Real hates it when you write septa. That's the French way, and he doesn't like it. Okay, yeah, he's kind of sticky about that one. Okay, 8, octa. Basically the same as all the shapes, guys. 9, nona. Okay, 10, deca. You won't need anything above that. Okay, questions on those? All right, so back to this here, okay, really the only thing you need to remember about molecular compounds is that they share their electrons, okay, and that makes their bonds really, really strong, okay, so electrons are shared, okay, between the two elements in a covalent bond, okay, that's the part of that that's kind of important. All right, so when we're naming molecular compounds, since there's no hope of balancing the negative charges, they can go together in whatever numbers are necessary for them to have full outer shells of electrons, okay? And that can be basically any combination as long as they're sharing the electrons. So we have to put in prefixes to tell everybody how many of each thing is in this compound. All right? So, for example, for this one here, I've got carbon and sulfur, both nonmetals. They're to the right-hand side of the staircase on the periodic table. Okay? So I write this as carbon disulfide. Right? The weird rule, the only one trick that happens in molecular compounds is if your first element is a 1, it doesn't get mono. Only the second one will get mono. The first one will get every other prefix, just not mono. For whatever reason, chemists have to be difficult and feel important, so they have to have tricky rules. Okay? It should be monooxide because it's a mistake. Yeah. Okay? Which I have every semester had someone point out and I refuse to fix for whatever reason. Okay, so dinitrogen, and this should be monooxide. Okay, or sometimes it's written like this, monoxide. Okay, either way, you can have monooxide or monoxide. Doesn't matter. Okay. It's fixed on your page, just not on mine. Okay, so I did get around to it then. Okay. All right. Okay, and then of course we end the second element in ide. Okay, the first one, whatever one comes first in the compound, its name doesn't get changed. Okay, but we list the ide always on the second one. That kind of holds true for basically all types of compounds. Okay, so our prefix, or sorry, suffix or prefix. Okay, our prefixes will be di, tri, whatever those ones we listed there a minute ago. For a big one like this, okay, we would have tetraphosphorus because there's 4, decaoxide. 10 oxygens. Okay, that's what it would look like. Now, on your periodic table, okay, if you pull that out, there are some elements that are colored in. Okay, those are what we call the molecular elements. Okay, these are elements that bond to themselves when they are by themselves. Okay, if there's nobody else to bond with, they bond with themselves. They're people that just can't be alone. Okay, these are elements that just can't be by themselves. They got to always be holding somebody's hand. Okay, so they are all of the elements in group 17. Okay, fluorine, chlorine, bromine, iodine, and astatine. Okay, as well as nitrogen and oxygen, also in yellow. Hydrogen is also in yellow. Okay, those ones pair up with themselves. Okay, that's why we always write oxygen as O2. Okay, it always pairs with itself when it's by itself. Right? We don't change its name. We don't call it dioxide. Okay, it's just oxygen. That's how oxygen comes in its natural state. Okay, and it's the same with nitrogen. It's the same with fluorine, chlorine, all of those. Okay, also listed in there, you have phosphorus, and I believe it's in blue, right? Okay, phosphorus is in blue, okay, because it comes as a 4. Okay, it'll bond with itself 4 times. Okay, make a tetrat, okay, or something like that. Okay, and sulfur bonds with itself 8 times. So if it's by itself, it's S8. Okay, pretty rare, okay, but it happens. Okay, they only do that when they're by themselves. In a compound, they can have any number that is necessary. They're only written that way if they're in their element form. All right, everybody follow me there? Okay, because I have people that often over-apply those numbers. They insist that any time oxygen is in a compound, it's got to be a 2. It can be whatever number it needs to be in that compound. It's only a 2 when it's by itself. All right. Let's look at the first one here. So I've got nitrogen and I've got iodine. Molecular compound because they're both non-metals. So if I'm going to name that, okay, how many nitrogens are there? 1. Okay, so I don't need to put a prefix on that. It's just going to be nitrogen. And then I is iodine, but since it's the second one, it's going to be changed to iodide, but what prefix does it need? Tri. Okay, you don't necessarily have to put the hyphen in. I just kind of do it out of habit. It looks weird to have 2 I's together. Okay, is that making sense? All right, these ones are easy. Do all 10 and then we'll go through them together. Okay, so it's write the name of the first one. If it needs a prefix other than 1, okay, it gets it. The second one gets whatever prefixes it needs, okay, and ends in "ide." Eric. Yes, all lowercase. Okay, so for our second one here, we've got carbon with 4 iodines. So this stuff is going to be carbon tetraiodide. Okay, and for this one here, we've got nitrogen with oxygen. They both have numbers on them, so they're both going to need prefixes. This is going to be dinitrogen trioxide. Okay, and then for number 4, we've got tellurium with astatine, so that's going to be tellurium, because the first ones don't get a prefix. Okay, if it's mono, okay, tellurium diastatide. Okay, and then for number 5, we've got phosphorus together with sulfur. They both have numbers this time, so not nitrogen, diphosphorus. Okay, trisulfide. Okay, remembering that all of these do have to have lowercase letters. Okay, they can't be capitalized because they're not proper names. Okay, how many people have done all 10? Okay. All right, so for number 6, I've got 1 oxygen and 1 sulfur. So this is going to be oxygen monosulfide. And then for number 7, I've got 3 silicone with 4 phosphorus. So trisilicone triphosphide. Sorry, trisilicone tetraphosphide. Okay, for number 8, 1 sulfur, 2 chlorines, sulfur dichloride. Okay, for number 10, 1 silicone, 4 hydrogens. Okay, hydrogen's acting as a non-metal here because it's listed second, right? If it's listed first, this would be an ionic compound then. Okay, this is still molecular because it's listed second. So we've got silicone tetrahydride. Okay, and then lastly, I've got boron with carbon. Okay, so that's going to be tetraboron tricarbide. Okay, questions on any of those? Okay, really the molecular ones are the easiest. As long as you can remember your prefixes, there's not a lot of thinking that goes on for them. Okay. Okay. All right, now, these are some ionic, some molecular, but there's a couple on here that we haven't talked about yet. Okay, so I want to go over 9 and 10 and that type of compound. Okay, number 9, what kind of compound is that? It can't be both. Is calcium a metal or a nonmetal? It's a metal. So what kind of compound is it? It's ionic, okay? As long as they have a metal in them, okay, and it's listed first, it's ionic, okay? This here, if you look on your periodic table, there's a little chart kind of in the middle at the top, okay? And it says table of common polyatomic ions, or, yeah, table of common polyatomic ions, okay? This is actually sulfate, okay? SO4 is sulfate, SO3 is sulfite, okay? So this stuff here, basically all I have to do is look up those polyatomic ions in that chart and write their name exactly as it appears in there. So this stuff would be calcium sulfate. Don't have to change the name. It's already written in its ionic form. You just write it out, okay? The challenge is you just got to find it, okay, and write the name. They're actually quite easy to name once you realize what you have to do. Okay? No, because it's ionic, and ionic compounds don't have prefixes. No, it's already written as it should be. Because if I write this as sulfide, that's something else, right? I can't change it to IDE because that already stands for S. Okay, that's why we have to leave it as whatever it is in that chart. Okay, so what would this stuff be then? Potassium with MnO4. Permanganate, yeah. Potassium permanganate. Okay, this is little tiny purple crystals. Okay, is what potassium permanganate looks like. They're actually quite pretty, but you don't want to touch them because when you do, they react with the oils on your fingers and stain your fingers brown for a long time until that skin wears off, until you exfoliate that stained brown skin. Okay, yeah. So if you have really light colored skin and you touch this stuff, your fingers are going to look really gross for a while. I once had a kid who never listened to me. This kid, I had to tell him everything like 5 times because he just never listened. Okay? He went into a lab and we were doing an experiment with this stuff, and I had told the whole class like 4 times, don't touch the potassium permanganate with your bare hands. He comes over to me with a tray of it. Mr. Coder, this stuff is so cool. He's just playing with it with his bare hands. I'm just laughing because I know in about 5 minutes his fingers are going to be that color brown on the tips, okay? And they're going to be that way for several days, okay? And he's like, well, you didn't tell me that was going to happen. And everybody in the class is like, yes, he did, doofus. Yeah, okay? So, yeah, don't touch that stuff. They actually used to use this as an antifungal. They would put it on your feet if you had athlete's foot. Then your feet would turn brown. But it killed fungus really well, okay? Just had the unpleasant side effect of turning your feet brown. As long as you didn't wear open-toed shoes, you were okay. If you wore open-toed shoes and you didn't already have kind of dark skin, then your skin looked kind of weird. Okay? All right, so give these a try. Remembering, though, that there's some molecular and some ionic in here, and maybe some that need Roman numeral. No, there aren't any that need Roman numerals. Okay? There's just some ionic and some molecular in there. How do you tell the difference? Look for a metal. If it's got a metal listed first, you follow the ionic rules. Okay, I'll give you a couple minutes on those. Okay, so just quickly here, Carson brings up a good point. Number 8 has 3 elements in it. Okay, if it's got 3 elements in it, then it most likely has a polyatomic ion from that little rectangular chart at the top. Okay, we know that sodium is an element, a metal by itself. Okay, and then that these 2 things must be together in the polyatomic ion chart. And if we look up there, we can see that OH is listed up there. This stuff is called sodium hydroxide. It's actually the stuff that's in oven cleaner. If you've ever used oven cleaner, that smell, that kind of stinging, burning sensation in your nose is this stuff. It's extremely basic, highly corrosive, which is why it eats the stuff off the inside of your oven when you put it in there. Okay? It would also eat the skin off your bones were you to get it on your fingers. That's why you're supposed to use rubber gloves and not inhale the fumes. Okay? There's one of these that does need Roman numerals. Which one? Yes, number 2. Chromium can be a 2 or a 3. Okay? That's one of those things you always got to look at the box when you're looking at it. Okay? When you look up the name, look at the box and make sure it doesn't have 2 charges. Okay? Chromium does have 2 charges. So, fluorine is always a -1. Since there's 3 of them, that's 3 negative charges. So chromium has to be a +3, right? To balance off the 3 negatives, it's got to be a +3. All right. Chromium, 1, 2, 3, fluoride. All right, how many people are done to number 5? Okay, let's go through the first 5 then. Okay, so for this one here, lithium with chlorine, is that ionic or molecular? It's ionic because lithium is a metal, so this stuff is simply lithium chloride. Okay, no prefixes. We don't use prefixes in ionic compounds. Okay, we already did number 2. Number 3, I've got phosphorus with bromine, ionic or molecular? That's molecular. Both of those are nonmetals. They're both right of the staircase, so this one's going to need prefixes. All right, well, we don't need one for phosphorus because it's only a 1. Okay, so phosphorus tribromide. So that's kind of the process you got to go through, the thought process you got to go through when you're looking at these. Is it ionic? Is it molecular? Then apply the right set of rules. Okay, zinc with iodine, ionic or molecular? Ionic. Zinc is a metal. Okay, so this stuff is going to be zinc iodide. Okay, no prefixes. And then for number 5, I've got silicone with oxygen. Ionic or molecular? It's molecular. Silicone is to the right of the staircase, just to the right of it, but it's to the right of it. Okay? Silicone dioxide. Okay? All right, give you a few more minutes and then I'll do 6 to 10. All right, let's have a look at 6 through 10 here. Okay, so for number 6, I've got carbon with sulfur, ionic or molecular? Molecular. They're both right of the staircase. Okay, so I'll need prefixes, but not on carbon because there's only one of it. Okay, carbon tetrasulfide. Okay, and for number 7, okay, we've got technetium, which is a man-made element, doesn't exist in nature. Okay, bonded with iodine. Okay, ionic or molecular? Ionic. Technetium is a metal. Okay, so iodide. Okay, we already did number 8. Okay, we said if you have more than 2 elements, you know you've got a polyatomic ion involved and you need to go up to the chart to find it. Okay, oftentimes polyatomic ions are going to be enclosed in brackets, but not always. Okay, in fact, for this one, it really shouldn't be. Okay? We usually only use brackets if we need to put another number outside of them so that we know the whole, this number here, this 2, applies to the whole thing. Okay? All right, so for number 9, I've got calcium with sulfate. Calcium is a metal or nonmetal? Metal, so this is an ionic compound. The other thing is, if you have a polyatomic ion, you are dealing with an ionic compound. Okay, so we've got calcium sulfate. Okay, is the name of this. Remember, we don't change the name of the polyatomic ions. All right, for number 10, we talked about that a minute ago. This is the purple crystals that turn your fingers brown. Okay, this is potassium permanganate. All right, number 11. Oh, sorry, I said I was only going to go to number 10. How many people have done all 15? Okay, I'll give you a couple more minutes. All right, so for number 11, I've got nitrogen with oxygen, ionic or molecular? Molecular. So this is going to be nitrogen monoxide. Okay, for number 12, I've got beryllium with cyanide, ionic or molecular? Ionic. So we got beryllium cyanide, okay, which is highly poisonous. All right, barium cyanide. Okay, we got barium, we got cyanide here. It's an ionic compound. Okay, we don't need any prefixes. Also, highly poisonous. Anything with cyanide in it is bad for you. Okay, number 14, we've got sodium with HCO3. Again, we've got more than 2 elements here. So one of these is a polyatomic ion, and it's HCO3. This stuff is sodium hydrogen carbonate. What's the common name for that stuff? Baking soda. Okay, and then 15 PO4, it's molecular. Okay, this is phosphorus tetraoxide. Now, occasionally, I have people who see that this same combination is in the table of polyatomic ions. And up there, it's called phosphate. How do I know it's not phosphate here? Yeah, it's by itself. Okay? It can only be phosphate if it's in a compound with something. If it's by itself, this is phosphorus tetraoxide. Okay? There are very rare occasions where that happens. Okay? Very rare. Questions on any of those? Okay. Now, next step, taking the name, going to the formula. Okay? This is where you do that drop and swap thing from last year. You only do that for what kind of compounds? Ionic. Okay? Molecular compounds, writing the formulas are really easy because you just look at the numbers and write the appropriate, or you look at the prefixes, sorry, and write the appropriate numbers. Okay? So they're pretty straightforward. Okay? First thing you got to do is read the name and decide, is this stuff ionic or is it molecular? And we can tell that by the presence of a metal. If there's a metal involved, we're dealing with an ionic compound, and then we're going to have to use the drop and swap. Okay? So that's what these steps are talking about. If you're dealing with an ionic compound, write the formula for the metal and indicate its charge. So if I was dealing with, let's say, for this one here, for calcium and chlorine, okay, I would write calcium, 2 plus, chlorine, 1 minus, and then drop and swap. So the 2 comes down here. This is a 1, it goes here, but we don't write 1s. There's the formula for calcium chloride, CaCl2. Okay, is that pretty straightforward? Okay, places where it can mess with you a little bit. If I have manganese 4 oxide, let's say, so let's say that's the title I got. Manganese 4 oxide. All right, so I write manganese, Mn, and what do I write beside it? 4. That's what the Roman numeral is there for, to tell me, use the 4, not the 2. Okay, that's why we put those in there. All right, so I go manganese plus 4, and oxygen minus 2. All right, now I drop and swap. 4 goes here, 2 goes here. Am I done? No. Can I reduce those? Then I do. Okay, and I end up with MnO2. Okay, it happens once in a while, but you got to be ready for it. Okay, we always reduce down to the lowest terms. Carson, you can't have negative atoms, right? Because then they have less than nothing. Yeah, so you always just take the absolute value of the numbers that are going down. Okay, because otherwise you're saying I have less than nothing, and you can't have that, right? All right. To write the chemical names for molecular compounds is even easier. Okay, it's just a matter of read the prefixes and write the appropriate number. All right, so for carbon disulfide, I've got 1 carbon and 2 sulfurs, CS2. Okay, for tetraphosphorus decaoxide, tetra means 4, deca means 10. Write them in. Now, why didn't I reduce that one? Because I can't. Right, it's molecular. I can't reduce molecular ones. It gave me those numbers. I keep those numbers. We only reduce the ionic compounds. Okay. All right. So I'll make up a couple here and you guys can try them. Okay, so I'm going to write names. I want you guys to give me formulas. I have 2 3s there. Nickel can be what? 2 or 3. Oh, that made it worse. Okay, let's look at our first 4 here. Sodium nitride, ionic or molecular? It's ionic because sodium is a metal. All right, so I'm going to write sodium with a +1, okay, and I'm going to write nitride. And nitride is always -3. So when I drop and swap, I'm going to end up with Na3N because we don't write the 1s. Okay? Everybody with me there? Okay. Questions on that one? Don't be afraid to ask. If you don't get it, ask. Okay. You follow what I did? Okay, except that we got to swap it before we drop it. Okay, the 3 was on the nitrogen to start with, right? Here's really what we're doing. If you recall, back when we did the Roman numerals, we were trying to make the charges balance out, right? Okay, so if sodium is always a +1 and nitrogen's always a -3, how many sodiums do I need? 3, right? That's why the swap and drop works. It always just it's way easier than thinking about that and doing the math every time. Swap and drop just makes it a lot quicker. Yeah? All right, so for number 2, okay, we got diphosphorus trioxide, ionic or molecular? Molecular, it's got prefixes in it. Okay, how many phosphorus? How many oxygen? 3, those are easy. Okay, all right, number 3, I've got calcium oxide. It's ionic, so calcium is a +2, oxygen is a -2. Does that already work out? Yeah, so if I drop and swap, I end up with 2 and 2, which can be reduced to just 1. 1's actually, but yeah, we don't show it. Okay, if it already works out and it's already balanced, you don't have to show any numbers. CaO. Okay, now we got a Roman numeral. That's only going to happen in what kind of compounds? Ionic. So copper is Cu, and the Roman numeral tells us this is the copper that's 2+. Okay, chlorine is always a -1. So I take the 1, I put it here. I take the 2, I put it here. CuCl2. Okay, Eric. Yes, always metal first, non-metal second. Basically the way it's written, do it in that order. Yeah. Okay, how many people are done to number 8? All right, so let's go over them all then. Okay, carbon monofluoride, ionic or molecular? Molecular, okay. Carbon with 1 fluorine, looks like that. Okay, and then nickel 2 hydroxide. All right, we got a Roman numeral, so it's definitely ionic. Nickel is Ni, and they told us it's a +2 charge. Then we got hydroxide, which is in our table of polyatomic ions as OH. This is something I didn't teach you yet. Okay, if I do the drop and swap, okay, this is a -1, so I put the 1 there. Okay, I'm done with that. I take the 2, I put it here. Is that right? I got to put it in brackets. Here's why. If I leave it this way, it's saying I have 1 nitrogen, 1 oxygen, and 2 hydrogens. But I want to have 2 hydroxides, so I have to put it in brackets. Anytime you have to put a number beside a polyatomic ion, you have to put it in brackets. Okay? Now, sometimes those polyatomic ions already have numbers. Then you enclose that number as well in brackets. Okay? The number that they come with doesn't change, right? So if we're looking at potassium sulfate, okay, we have K with PO4. Okay, that number isn't going to change, right? I'm not going to change that to a 1 because potassium is a 1. Okay, I don't change it at all. In fact, okay, I'm going to use phosphate's a -3, right? Okay, so I'm going to have K3PO4. I don't even need brackets because I don't need to put a number beside the 4. Okay, everybody follow me on that one? Right, and then for number 7, ammonium chloride. So if we look on our periodic table there, ammonium is NH4, and it has a +1 charge. Okay, chlorine is always a -1. So does that one already work out? Good. Just NH4Cl. That's about as tricky as they get. No, I don't need to put brackets around NH4 because I don't need to put another number beside it. Okay, now that's a good question. Had this, instead of being ammonium chloride, been ammonium nitride, then I would have this, NH4, okay, this is a +1 and this is a -3. Now I need to put brackets around NH4 so that 3 goes beside it. Okay, otherwise I'd have NH43, which means a lot different than NH4 bracket 3. Yeah? Okay, everybody with me there? Okay, now I think we'll leave it at that for today because I want to talk about the next couple of days. Okay, I'm not going to be here the next couple of days because I'm off with the basketball team.